Welcome to the 16th lecture for Physics 4C. In this lecture set, we will look at some exam type questions involving special relativity, but not quantum mechanics yet. First, a quick topics review of what we have covered in the last 3 weeks. One benefit of a review is that we can skip much of the introductory materials that were necessary for motivating and justifying certain lines of thinking. For example, since the two postulates of special relativity are encapsulated in the Lorentz transformation of spacetime, we can simply start there. I do want to remind you of certain simplifications that both help you memorize the Lorentz transformation and highlight the symmetries preserved by it. To start, defining gamma equal to 1 over square root of 1 minus v squared divided by c squared, and using it in the transformation simplifies its appearance. And further defining beta equals v over c simplifies it more. And using the matrix multiplication representation really simplifies the Lorentz transformation, where it comes down to remembering the arrangement of space-time 4-vector with the time component coming first, expressed as c times t for dimensional consistency, and followed by the 3 spatial components. And remembering the 4x4 symmetric matrix that represents the Lorentz transformation. A lot of what we do in special relativity involves this transformation, drawing space-time diagrams, and reasoning through special relativity paradoxes are all applications of this one transformation. A lot of practical problems in special relativity will involve some dynamical interaction, usually a collision or a decay that involves change of relativistic energy and momentum. So, you should remember the derived expressions for the relativistic momentum equal to gamma times mv, and for the relativistic energy equal to gamma times mc squared. And remember, this includes the rest energy that you get when gamma is equal to 1. In many problems, Lorentz transformation of energy momentum 4-vector will be useful, along with the Lorentz invariant for the 4-vector, which gives you the invariant mass, also known as simply mass, or rest mass if you're trying to clarify it for someone still using the outdated notion of relativistic mass. There are some other formulas that if I were walking into a closed book exam, I would want to have handy on a formula sheet, because it takes time to derive them from first principles. I have the examples of the relativistic velocity transformation rule and the Doppler effect formulas here. But the most important things, such as drawing spacetime diagrams and tips and tricks in analyzing relativistic collisions, are not represented well by simple formulas. So, for those, we have 4 examples of exam-type special relativity problem solving. I'll refer to them by their question title: Relativistic Train, which deals mostly with relativistic kinematics and working through a paradox type situation; Dynamics of Particle Decay, in which decay of a hypothetical particle is analyzed in a couple different reference frames; Beta Decays, in which dynamics involving muon and neutron beta decays are worked out; and Particle Accelerator Physics, in which collider arrangements are analyzed.
So when we come back from the break, let me start out with this. A relativistic train through station. That'll essentially be the past sample exam that's posted. So you could read it, but that will be your written record when you're studying on your own. So the first question I thought we would go over is this question on the posted sample exam. It's a good overview of the relativistic kinematics and some things that actually do relate a bit of relativity paradoxes that if you get confused, that's a good indication that there's something for you to review here. So let's go through this. This long thing of stuff, it's describing essentially this setup. You have a train station, which is at rest, and this defines your, let's say, your non-moving frame. This is my frame S. And the train, that's the one that defines my primed reference frame. It's moving at speed v relative to this at rest thing. And it's going to pass by this station without stopping. Okay? So part A asks for, and I guess all the rest of these are, what it's saying is this. The coordinate systems are arranged so that so if this is the midpoint of the train, then the time and position coordinate systems are arranged so that at time equals 0, which would also, at time equals 0, this point would coincide with this point here. So at time equals 0, x prime is equal to x equal to 0. Or how do I? Well, let me, without writing this down, let me just put it that this midpoint of the train is coinciding with the midpoint of the train station. Okay? So this is a quick intuition check. So at time equals 0, from the perspective of the station, how do you think this train should appear? Should it be shorter than the train station, or should it be extending out beyond the train station? Shorter, right? You expect this to be Lorentz contracted, and that is the correct answer. And so let me just draw this. So at time t equals 0, this is what you should see. And it says, as described the front end, give the space-time coordinates for the front and back of the train in frame S at time t equals 0. All right, let's try that. So this is the Lorentz transformation for part A. Ct prime is equal to gamma Ct minus beta x, and x prime is equal to gamma x minus beta Ct, right? So let's plug in the numbers we have. So we have two different points, the front and the back. Let me call the front, I don't know, F, and the back, B. So we are looking for the coordinates, x front and x back, right? When you look at this, you run into a little bit of an, well, actually, maybe you don't. Let me plug in the numbers and see. So when you plug in the numbers for the front, for example, then this is what you get. All right, so for the, actually, let me ignore the first equation, because I'm seeing the first equation is not giving me what I want. I'll just use the second equation. So with the second equation, what I get, x prime front, so that will be just plus, so let me write down the intermediate step. X prime front is equal to gamma. Did I say I could leave the answer in terms of gamma and b? Oh, I didn't. Yeah, gamma and x front, so this is the coordinate I don't know, I'm trying to find out, minus beta c, what's my value of t? 0. It's at time equals 0, so this is just 0. So I can just solve for, this is known, the x prime f is plus L over 2. So my x coordinate, x front, is equal to plus L over 2 divided by gamma. So L over 2 gamma. And as you remember, gamma is greater than 1. So this number is smaller than L over 2. So this is XF, which is L over 2 gamma is less than this. It fits within the station. And if you did the back, then it would be the same thing, except for this number will be minus L over 2. So this value would be minus L over 2 gamma. So the same thing again. Good? So all of this is good. So A is supposed to be easy. It's your intuition. It's a B where you have to be more careful. So B is asking you to describe the situation not from the perspective of the train station, not from the perspective of the train station, but from the perspective of the train. So it's a very important distinction. It says, so he looks at t prime equals 0. When the middle of the space train coincides with the train station, whether he released space buoys, blah, 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 so that they are at rest relative to the train station. So this is what we are trying to look at. So let's just say, leaving this. So for part B, we are trying to describe this exact same physical situation, but from the reference frame of the train. So from the reference frame of the train, this is what you should have. So you have the train that's actually at rest. This is my x prime equals 0, and x prime equals L over 2 minus L over 2. And from the perspective of the train, what you see is that the train station is approaching you at some speed v. So the coordinates are still set the same way. So if this is the midpoint of the train station, then at t prime equals 0, this midpoint of the train station is supposed to coincide with the midpoint of the train. So this is that's worded a little bit differently, but this is what the question comes down to. At t prime equals 0, where are these front and back of the train station relative to the front and back of the train? Are they beyond this front and back of the train, or are they inside? So does the train, fit inside the train station, or does it overflow the train station? Overflow. So for people who said it overflows, what's your, how do you get that answer? Yeah, the train station is moving, so you say, all right, moving things are shorter. So you say at t prime equals 0, that this is how it should appear. Well, let's see if that's the answer. Let's have the answer first and then try to make a sense of the answer that we get. And this is a place where if you want to be absolutely sure you didn't make a mistake, you use Lorentz transformation. You could technically get the correct answer using length contraction, but that won't help you answer the next two parts. So this is what the Lorentz transformation says. It's the same expression we had before. Ct prime is equal to gamma Ct minus beta x. X prime is equal to gamma x minus beta Ct. Now the difference here is, so before we knew what the value of x prime was, right? And we were trying to find the x. But this time it's different. So for example, if we are dealing with the front here, x front, then we know what the value of this is. That is L over 2. And this xf prime, that's the unknown. So you look at these two, and let's say you were to look at the same equation we used the last time, and you try to do the same thing, all right? So x prime f is equal to gamma xf minus, is this still 0? This is where you have to be careful. It said t prime equal to 0. In other words, this is equal to 0. You don't have a guarantee that t is equal to 0. This is what, so when you use Lorentz transformation, at some point you should realize that simultaneity is relative. Because t prime is equal to 0 doesn't mean t is equal to 0 at any points other than this midpoint. So this is where you have to be careful, you know. When you look at t, don't say t is equal to 0 because nowhere in this setup said that t is equal to 0. It said that t prime is equal to 0. So you really should leave this as it is. It's a beta ct, which means, oh, so we cannot solve for xf quite yet. We have to figure out what this t is and then plug that in to actually finish it. So that's where we go back to the first equation. This time, unlike here where we didn't know what this was, we know this is equal to 0. Because the setup said that t prime, we are looking at t prime equal to 0. So this is equal to 0. So I can solve this for t, I think. So that means this whole thing is equal to 0. So if I solve for t, then t is equal to, move this over, beta x divided by c. Right? In hindsight, that probably makes a bit of sense. That sort of how much time, maybe it doesn't. You know, I don't know if it should make sense. But that's the value of time. That's the value of t, time for that space-time event coordinate in the frame S. So to calculate this, now you plug this in here. So you get gamma xf minus, plugging this in, I have beta squared. C's cancel out. So it's a beta squared x. So value of x would be xf. xf. Good. I can factor out xf. Can I simplify this more? What is gamma times 1 minus beta squared? Not 1. No. If it's gamma squared times 1 minus beta squared. Because, yeah, it's gamma is 1 over square root of 1 minus. Yeah, so this is equal to xf divided by gamma. So now once again, we know xf, L over 2, and we're trying to figure out what x prime f is. And x prime f is equal to L over 2 gamma. So you get the answer that you intuitively expect if you are saying that, all right, this is where I'm observing from, and the moving train station is shorter. And the answer you get does say, yeah, it is shorter. This is equal to L over 2 gamma. But when you use Lorentz transformation, what I'm hoping that you would see is exactly how these two pictures are consistent with each other. Because these two pictures are both describing the exact same thing. As in, look at it this way. So you have this physical event. You have this physical event of two cars passing each other. This is the car at rest. You could think of this as your train station, and the other car is passing by it. And as it passes by, the question you are asking is, which of these two cars are shorter than the other? And the somewhat paradoxical answer we have is that, well, if you are riding here, you see this car moving past you, this is shorter. But if you are riding here, and as you are moving past here, as you look at the other car looks shorter than you are. So which is shorter? They can. So this is where the paradox comes in, because the intuitive response you would give is they can both be shorter than each other. But really the thing that our intuition misses out on is the fact that simultaneity is relative. So as this car passes through, you measure its endpoint at t equals 0, simultaneously in this reference frame. And what that is different from what the observer on the moving car would say is simultaneous. All of this is a lot easier to illustrate on a diagram rather than, you can write it out in equations, but sometimes you see, sometimes you don't. That's really what the next question on this exam question was. So I probably cannot ask the exact same question on your exam, because here I'm explicitly asking people to draw space-time diagram to explain this. So let me at least draw the space-time diagram so that you can kind of see what I'm trying to illustrate here. So this is the axis for the space-time diagram. The x-axis and the time ct axis. Yeah. And I guess I could tie what I'm, this is all reminder, but I can tie what I'm going to draw with something that you have seen. Let me point to the correct one. Lorentz transformation. So Lorentz transformation says that x prime is equal to gamma x minus beta ct, right? So let's consider a line that's defined by a set of points which have the coordinate x prime over equal to 0 at different times. So then you have this equation, 0 is equal to this, that relates x and t, or x and ct rather. So let me write it out this way. Solving it for ct, you get ct is equal to x divided by beta. So on this axis, this would be represented by a line of slope 1 over beta. Okay. Let me draw that line. So this is the line of the slope. This is the slope of 1 over beta. And what do we associate this line with in the space-time diagram? You could say this is the word line of the object that said x prime equal to 0. And that also happens to define the ct prime axis. Because ct prime axis is consisting of the points that have value of x prime equal to 0. Ct axis is where x is equal to 0. Yeah? All right, so that's one. Let me do another one. So this time I actually want the x prime axis. So this x-axis is set of points where ct is equal to 0. So let me do that. So I'm looking at the first equation here. Ct prime is equal to gamma ct minus beta x. So if you say, all right, my t prime is equal to 0, then the equation you have is ct minus beta x is equal to 0, or from that you get ct is equal to beta x. So, you have just this equation, ct is equal to beta x. What slope does this line have in your axis of ct and x there? Yeah, beta. So you get the simple line here. So if beta is 0, it would be flat. So if beta is something not 0, but not quite 1 either, then this line has a slope of beta, and this is my x prime axis. So these are the space-time axis in my space-time diagram. And this is the axis I would use to illustrate the events that are going on here. So let me start the description this way. So I guess I can start with, let me try to represent the station at time equals 0. So at time equals 0, I have one end of station here at x equals L over 2. The other end of the station here at x equals minus L over 2. These are the space-time coordinates of the endpoints of the station, right? At other times, at different times, how do these endpoints travel on this space-time? What do the trajectory of these endpoints look like?
Like vertically?
Vertical, right? As in, it remains at this x coordinate forever. It doesn't go anywhere. So here, if I'm just drawing it, it would look just vertical. All right, so this is the word line of the front and back of the station. I don't think I drew it evenly. Oh well. And let's see. I guess I didn't draw the unit scale, so it you're just gonna take my word for it when I put these points where I'm gonna put them. So this is the end point of the train at t prime equal to 0, so that I can mark them along the axis here. So at t prime equals 0, this would be the front of the train. And at t prime equals 0, this would be the back of the train. Yeah? And how do these front and back of the, I didn't quite draw this right. Sorry, it's a lot easier to, sorry, I didn't quite draw this to scale. I think it should be somewhere here. That'll be easier for me to draw correctly. So in this way of drawing, what does the trajectory of the front and back of the train look like? It's parallel with this axis, right? Because it's moving with the middle of the train. So when you draw this word line, it should, yeah, I'm not, sorry, I didn't draw this quite right. It's a lot easier when you are graphing this on a computer. So let me just do my best, and we'll just kind of talk through it, what all this means. So this is the front of the train. This is the trajectory of the front of the train, and this is the trajectory of the back of the train. Good? So so this is the full explanation of what's happening as the train passes through the train station. So at t equals 0, at time equals 0, the train station guy makes a note of where everything is. He notes, where front and back of his stuff are, but that probably wouldn't really matter because it's not moving anyway. So whether he measures at t equals 0 or some later time doesn't make a difference. It's the moving object where he has to be more careful. When he looks at the front and back of the train, it's important that he measures them at t equals 0. So what the train station guy does is he gets the position of the front and the back of the train at exactly t equals 0. T equals 0 here. So you can see it a little bit better here. You can see that the back of the train has passed through the back of the train station. So train fits inside the train station. So as measured by the train station guy, this is the train. This is all the points that's along the train at the snapshot taken at time equals 0. You know that it's time equals 0 because it's along the x-axis where it's all t equals 0. Now, what the train guy, not the station guy, what the train guy observes is that t prime equal to 0. And that's what makes all the difference. Instead of, so instead of measuring the position of the, at t prime equals 0, okay, so this is where the back and the front of the train is. And in his own reference frame, So at t prime equals 0, the space-time coordinate of the station that he's using for his measurement is this point here. This is the back of the train, back of the train station at t prime equal to 0. This is the front of the train station at t prime equals 0. And you see that along this line of simultaneity, which is different from the line of simultaneity used by train station guy, the length of the train station fits within the length of the train. So, so that's the explanation of it. And I guess I don't know how much time you want to spend on that. So I will just leave you here. I think this is one of the first things I said as we were going into special relativity. Much of the confusion about special relativity, which we call special relativity paradoxes, it stems from implicit assumption about absolute simultaneity. When you get used to the idea that relativity simultaneity is relative. That what's simultaneous in one reference frame is not simultaneous in another reference frame. Then the things that you are used to thinking of as paradox shouldn't be paradox anymore. There's a way to describe it so that it's in a perfectly self-consistent way. You don't have to ask the meaningless question of, well, one of these two must be shorter than the other. Well, you could also say they must have absolute simultaneity, but they don't. So when you're measuring length, that relativity of simultaneity is going to affect how you think about the length of things. Yeah.
The questions you see here are questions that I basically programmed in from past midterm exams. And the 20-minute amount of time, it's again a bit tight. It's closer to the amount of time I used to give for midterm exam, as in usually the midterm exam was structured in a way. You're about an hour you're supposed to spend on multiple choice. The other hour you're supposed to spend on free-form portion, and I usually had 3 free-form questions. So 20 minutes, that's about right. What you lose out on in this format is the flexibility, because sometimes people would finish the multiple choice questions a lot more quickly, like in 30 minutes, and have more time left over for free form. Or sometimes as you're doing free form, you'd recognize a question is difficult, skip it, do the other easier questions first, and with the more difficult question, you would have, 40 minutes to work on it. And in this format, it's just something that you lose out of, that you don't have that flexibility. That most of the questions should be of similar difficulty, but there's some variation, and even if you are unlucky enough to get harder question, you will still only have 20 minutes. I think the balancing thing will be the add work feature. It's available after you submit your answer. So during the 20-minute time limit, really your focus should be getting to the correct answer and putting it in the answer box as a proof of what you have completed during the 20-minute time limit. And if you need to organize your work and make everything neat and understandable from someone else's perspective, you should do that after the 20-minute time limit. So with that, I'm going to start. I don't know what question I'll get, other than it's a random question from the poll. Oh, let me start here. Okay, so this is the question. It says, consider a hypothetical unstable particle of some mass decaying with 2 identical particles. Okay. All right. So the picture that they are asking us to consider is, so I have some particle of some mass, and this would be before, and after whatever interaction is going on, this particle breaks up into 2 identical particles. So there's 2 m's, There's a 1m on another m, and they split up. And now, as you are looking at these numbers, if you're looking at 2m, that's less than m. Hopefully by now, after last week's coverage of special relativity dynamics, the fact that your mass changes is not surprising to you. That difference in the mass is going to the kinetic energy of these particles that are flying apart from each other. So they are moving away from each other with some speed v. And so part A asks, consider the interaction in the center of momentum frame, where the total momentum of all particles in the system is zero. So in this picture, that just means, before the breakup, this was just at rest. It wasn't going anywhere. So that the momentum of the single particle could be zero. What are the kinetic energies of the two particles of mass m? Yeah. So here, as I was drawing it, I kind of intuitively gave them the same speed, and that's actually the way it has to be, so that the momentum will be conserved in this center of momentum frame, that the total momentum is equal to zero. So these two having the same speed, that's necessary to conserve momentum from the before picture in the center of momentum frame. So it asks, what are the kinetic energies of the two particles of mass m? Okay, I think that seems simple enough. So let me write out expressions this way. So I'm using conservation law. So I'm going to be using conservation of energy. So let's just write down expressions for energy. The expression for energy of the before would be, well, my total energy here was just the rest energy, mc squared. No kinetic energy, it's not moving, nothing. In the after picture, I guess I could write down the energy for one of them, and I just double it since it's symmetric and all that. So after the breakup, the total energy would be, well, whatever gamma corresponds to that, it'll be gamma corresponding to that speed v times the mass of the thing, c squared, and times 2, since there's 2 of them. So that's the total energy after the breakup. And what conservation of energy says is that this expression for energy should be equal to this expression of energy, because energy didn't change in the process. So mc squared is equal to gamma v small m c squared times 2. Okay. And it's so what is it asking? It's asking, what are the kinetic energies of the two particles of mass m? Well, the expression for kinetic energy. So if I'm just looking at this mass here, so the total energy is gamma mc squared, and we covered in the lecture how the way we like to look at kinetic energy is the total energy minus the what we have come to call rest energy. So gamma mc squared minus mc squared, or gamma minus 1 mc squared. And I hope you notice here that this gamma mc squared is already here. So I already have that. And mc squared only depends on quantities that I already know. So, if I'm kind of breaking up this expression on the right-hand side in terms of the rest energy and kinetic energy, the rest energy portion would be this, 2 mc squared. This is my rest energy. And the kinetic energy portion is basically whatever I need to add so that I come back to this. So that's going to be 2 times gamma v minus 1 mc squared. So this portion is the kinetic energy. Now, I guess the challenging thing here is that So when you look at these parameters here, gamma is not here. What do I do with the gamma? I hope it doesn't take you too long to look at it the other way, because really what you want is the expression for kinetic energy. So I can just look at the remainder, this here that I know, this here in terms of all the parameters there. So I can actually just solve for this kinetic energy, saying, okay, that kinetic energy piece is equal to the original left-hand side, mc squared, minus the rest energy, moving this over to mc squared. So this would be the total kinetic energy. And that's it. And I think a lot of people might be able to get to this expression kind of intuitively, the mass difference being kind of converted into kinetic energy, which, it's not incorrect. I might quibble with some semantics of it, but yeah, if you're getting at the answer here through that route, that's also fine. Here I'm just trying to do it more properly. So the total kinetic energy would be mc squared minus 2 times mc squared, or kinetic energy per particle is the half of that. So it will be m times the c squared over 2 minus 2 cancels out, small m times the c squared. And I'll attach the work quiz showing that, n given numerical value of the kinetic energy in electron volt units. That's where I look at these numbers, see the c squares will cancel this stuff out, and say, so total kinetic energy is just difference between them. Not 800. 1,000 minus twice 200, so 600 MeV, or K per particle, just half of that, 300 MeV. And C is cancel out. By the way, I think I randomized the question so that these numbers are not necessarily the same. So, read the question, actually work through it, even if you are lucky enough to get this exact question. 11 minutes. Okay, I gotta go faster. In this central momentum frame, what are the speeds? Oh, so this is a kind of a fun one. So this took me a long time to develop this sense of intuition for relativistic dynamics, which parameters are useful, which are less useful. So what we do have is the total energy for one of those small m particles is gamma mc squared. And I have a numerical value for that. So, the kinetic energy of a particle is 300. Rest energy is 200, so that total energy is 500 MeV. And I already know that from the given values, mc squared is 200 MeV. So by knowing the total energy and by looking at what kind of change you need to get to gamma, knowing these two pieces of information, the total energy and the rest energy, actually gives me gamma right away. Gamma is 500 divided by 200, units cancel out, 5 over 2. That's gamma. And the reason I'm getting to gamma first, even though it's asking for the speeds, is because from having worked in this relativistic dynamics for a while, I realized that gamma is often the easier parameter to work with. And once you have gamma, it's just a single step remaining to work out any other quantity you want, like the beta, speed of the things in the as a fraction of speed of light. So you take this expression, gamma is 1 over square root of 1 minus beta squared, solve it for beta. When you have done that, you'll get beta is equal to 1 minus 1 over gamma squared, square rooted. So once I have gamma, I can just plug it in here. So yeah, it's saying what are the speeds of the two identical particles if their speeds as a fraction of speed of light. Yeah, but it's looking for a numerical answer. So let me just plug in the numbers. So square root of 1 minus 1 over gamma squared. So that would be 5 divided by 2. I'm putting that dot there to force a decimal approximation. Squared. So 0. Oh, I guess that's, I don't know. I'll just use three significant figures. V is equal to 0.917c. In this highly relativistic situation, there might be some other set of numbers generated where it might be more relativistic. Here, a little bit, not that much. Yeah. Okay, suppose that the hypothetical particle mass m is actually moving at that speed in the left frame. The particles of mass m are emitted along the direction. Yeah. What are the total? So this is it's a Lorentz transformation question. It's one of the ways that I would like you to learn how to handle special relativistic dynamics, which leans rather heavily on the knowledge that this quantity forms a four vector. It's an energy momentum four vector with energy in the, or energy divided by c in the time component of the four vector, like the coordinates, space-time coordinates, and the momentum forms the spatial three dimensions of that four vector. So once you fully get that, then you can use a Lorentz transformation on this. So if you want the the energy and the momentum values, so let me just deal with only the x component. If you want the values of energy and momentum in a Lorentz boosted frame, then all you need to do is take the energy and momentum in some original rest frame, where original reference frame where you know their values already, and apply the Lorentz transformation. Think the gamma minus gamma beta minus gamma beta gamma. If you know how to do matrix multiplication, then it's a rather simple calculation. So your Lorentz transformed energy is, I'm gonna work in units of c is equal to 1 because it's quicker. So gamma times that, gamma e minus gamma beta, the momentum component, and your Lorentz transformed momentum will be minus gamma beta e plus gamma original momentum. So yeah, let me just, so I think I'm just gonna do this in Sage Math, the rest of it. I guess if you are doing what I'm doing, then you should include the screenshots of your Sage Math or whatever as your work. So let me just declare some of the variables. I need the E prime, I need the beta, I need the momentum x prime. I think that's everything. Okay. So I didn't have to declare some of this. So the transformed momentum is gamma times E minus gamma times beta times px. Yeah. And my transformed momentum is minus gamma times beta times E plus gamma times the original momentum. Okay. So what are the total energies? Yeah, so I have to compute these separately. One of the particles will have more energy, and the other one will have less energy. So for one of the particles, I can consider the particle that was moving in the same direction as m. So for that particle, px should be in the same direction as that. Yeah, then px should be what I calculated above. So the gamma mv or gamma. So the important part is a plus gamma m beta c, and I'm going to be using that number that I calculated above of beta. So let me just copy and paste that as beta is equal to that. Oh wait, that's I need to track two different values. Okay, so I'm gonna do this. Px is equal to beta 2 is equal to that value. So because gamma and beta here, it refers to the relative velocities between the frames. What I'm referring to as beta 2 is it's the speed of the particles in the center of momentum frame. So, and gamma 2 should be 1 over square root of 1 minus beta 2 squared. Okay, I have that. So let's get the new total energy. So EP should substitute in gamma is equal to, let me substitute in beta first, which is 0.95. That's the number given here. And then substitute in gamma is equal to 1 over square root of, there are more efficient way to do it, but let me just do it this way so that I don't run out of time. And then I have to substitute in energy of, before we had 500 MeV for total, I think. 500 MeV for total. And for momentum, it's going to be that gamma 2 times beta 2 times the rest mass, rest energy is 200 MeV per c squared. So, gamma. So that's it. So I think that's actually the particle that's moving in the opposite direction. So energy of lower energy particle is 207.063 MeV. Energy of higher energy particle. So it's the same calculation. The only thing that you are changing is for the momentum, this becomes minus because it was going in the opposite direction. And it's a lot higher. Energy of the higher energy particle is 2995.5 MeV. And the speeds of the two particles, they are going to be very different. So, so once you have the total energy, then let me just do the calculation this way: 207.063 divided by the rest energy. That gives me gamma right away. That's what I was pointing out earlier above. So that's the gamma for the lower energy particle. So for beta, it'll be square root of 1 minus 1 divided by the previous output squared. That's the beta for that other particle. So speed of lower energy particle is 0.258895 c. Speed of higher energy particle, this is where you really have to put in a lot of significant figures to make sure that it's distinguishable from C. So it'll pull from the previous output and, okay, maybe not that much, just 0.9978 C. Let me just use the same significant figures. So, 8 seconds left. Use time dilation. Okay. Did it save? So, okay, saved. Okay, good. So, So, if I had watched the time, I would have gone through this a little bit more quickly so that I can work it out. So, because it's relatively easy, because given that you have gamma of 1 over square root of 1 minus 0.9 squared. That's gamma. So the time dilation, it's gonna be this factor which is greater than 1 times this. That gives you it gives you the lab lifetime. So this times 1 times 10 to the power of minus 6. So 3.2 times 10 to the power of minus 6. That's what the answer there is. So this is what I would recommend. if you see yourself running out of time, um, do put something in. That's why I put this in. Leaving it blank versus putting something in that's incomplete, it's two different things, because when I put this in, then I'm signaling that I know how to do it. I just ran out of time. Whereas when it's completely blank, maybe you didn't know what to do. That's always a possibility. So the lifetime, which is gamma times the proper lifetime, is equal to, with all these numbers using um, for beta equals 0.95 in the C, is the here the lifetime is 3.20 times 10 to the minus 6 second. So depending on the how much is missing, you might not get full credit, but it's always better to have something here than have a completely blank thing. And the work that you attach, that is not time limited. So especially if you find mistakes, or like, one of the things I'd like to double check is these two energies added together should be the energy of the hypothetical particle. Let me just double check that is the case. So the energy of the original particle should be gamma mc squared, and here the gamma is 1 over square root of 1 minus 0.9 squared. Yeah, that's gamma times mass of the particle was 1000 MeV, or c squared, and then times c squared, that cancels out. So yeah, so that's 3200. So that's the total starting energy. And these two added together should be equal to that, and I think they are. So good. I'm less worried about this being wrong. So yeah, it's you should organize your work. If you might have made mistakes within the time limit, it's totally okay for you to reflect that understanding in your attached work. The only thing that am holding you to is that you are still under the honor code. No outside help is allowed. So let me attach work. So in terms of work, what I will need to do is, let me just grab a screenshot of this and attach that. So that's for part A. By the way, I do recommend that you organize it a lot more than how much you semi-organize. Like this is all scratch work. You should spend a little more time organizing it than I am. I'm just rushing through it so that I can do some other stuff during this virtual class session. Part B. And for part C, I think this is how I'll have to do it. So I have this scratch work that's kind of illustrating the algebraic work that I have done and needed to add and have done. And the calculation itself, I kind of did it in Sage Math. And so I want to just make sure I include enough portion of Sage Math to capture that. So I think I'm using this value, yeah. So let me just go from here to, I guess I need this portion. This is just me writing out some of the things I need to do. Oh, wait, yeah, let me do through here. And then I'm just gonna skip over the error message. Like, I don't need to see your programming error messages. So the corrected expression here, yeah, and the rest and the captures that, yeah. That's just me double checking. That's part D. So I think through here is right. Yeah, all of this is my work for part C. So something like this. Mainly, so the goal of work always is I should be able to follow your reasoning process. And it especially matters when there might be mistakes, because oftentimes when I see correct answer and reasonable amount of work, I assume that you understood everything and you did everything properly, correctly. It's when the answer seems to be wrong that's where I kind of want to figure out where you might have gone wrong, so that I can give you the correct amount of partial credit. And that's where the more work you show, the better chance there is. I can figure out where you went off and give you correct, deserving amount of partial credit on the parts that you didn't really miss. So yeah, so that's it. Let me just save, work, and continue, and that's all there. By the way, especially if you're doing this towards the end of the due time, like if you're doing this Friday late at night, close to midnight, be careful that sometimes the system will kick you out while you may be attaching work. Now you do have access to this after the due date. Like if I just refresh it here, you'll see my access to add work. Like you can access this after you submit it, even after the due date. But I've had this issue in the past where while the students were working on the work to attach, they got kicked out because when the due date that boundary crosses, then system I think just kicks people out. So what you should be doing is what you've seen me do. Basically, I've done most of the work here, and here all I've done is copy and paste the work I've done elsewhere. Whether it's you're taking photo of something that you've written out and uploading it here, or if you're doing what I'm doing digitally. I guess the main point is you shouldn't be spending a lot of time typing things into this window where you could get kicked out and lose your work. If it's gonna take you more than 5 minutes to attach something, do it on some external software where you have better assurance that you won't get kicked out in the middle of working through that. All right, so I'm about to start the freeform timed assessment. And ahead of this session, I did look ahead to what questions test student will be getting so that I can make sure that that question won't be the same two questions that I've done before. So I kind of know what question I'll get when I start, but let me start anyway. So start, I gotta watch the time. 20 minutes is a short amount of time, even I don't have a lot of time to doodle and or waste. So we'll start. All right. Beta decay was the name given to radioactivity. Have I mentioned the beta decays yet? If not, that those details don't matter. What matters is that, for an example, following are the masses of particles you might. Okay, we are given some masses, and also okay. Enter text entry. All right. Consider the decay of a muon into electron and two neutrinos. What is the minimum energy the electron can have in this decay? For the the minimum energy electron can have is its rest energy is equal to me c squared. And the reason for that is we can consider the decay of the muon in the reference frame where muon was initially at rest, zero momentum. Then the total momentum of the decay particles should be zero. We can easily achieve this using the two neutrinos and technically antineutrinos to antineutrinos. Well, one is anti one. Okay, I'll just say two neutrinos, and all that matters is that they are all nearly massless particles. Two neutrinos. You just have the two neutrinos going the opposite side, carry the same momentum by sending them in diametrically opposed directions with the same momentum. The difference in energy between the muon and the electron can be carried away by the neutrinos. Yeah, that's it. Minimum energy is easy. What is the maximum energy? Okay, that's harder. Now we have to consider conservation of energy and momentum. So, all right, so let's do that calculation. So what I'll say is that it's going to be less than muon 105.7 minus 0.5 MeV, because some of the energy will have to go to the neutrinos to balance out the difference in the rest energies of the muon and the electron. Alright, so I have to set up the scenario. So this is what it looks like. Let me do part B. So I have a single particle, let me call it muon, and it's gonna decay into basically two particles. I know, so well, one of them will be electron. Let's say that's going to the right in speed v1. And the two neutrinos, if I want to maximize the electron velocity, then the two neutrinos should be basically adding in the same direction. So they will have the kind of the momentum point in the same direction. So what I think analytically cleaner is treat this like that's one particle that's going one way with some momentum P2. So I think we are treating the neutrinos as massless here. So if I say speed, it'll be speed of light. So I need to have its momentum. So, all right, so that's the setup. And I think I'm going to use the conservation principle. So that is conservation of for momentum. The energy momentum for vector. So in setting that up, I have left-hand side will be my initial. So the muon has some energy, mass of the muon times c squared. It's got no momentum if we are still analyzing in the rest frame of the muon. So 0, 0, 0 is equal to sum of these two momenta. One is belonging to the electron that it's decaying to. So the energy term of gamma MEC squared, and I'll label it gamma E so I don't confuse them later. And the momentum is gamma E ME MEV, let me call it VE. And you see the units don't quite match yet, and that's because by convention these components are written as like PC. So this is P and I need a C, but just C. And then the rest will be 0. So I got those for the muon and the electron, and in the final state, so you will find that this cannot possibly conserve both energy and momentum. So you need to have another particle that will carry away extra momentum. And that's going to be the muon. So treating muon as being massless, what it'll be is we'll have 2 times the energy of the muon on the energy component. And on the momentum component, I want to maximize this, meaning I will I'll maximize actually. So the momentum of the neutrino, I should write this minus momentum of the neutrino times C, and then 0, 0. So let's just do this algebra and see where it stands. I'm gonna add this and then set that element equal to this. So doing that, I get mu c squared is equal to gamma e MEC squared plus 2e nu. How much time do I have left? 12 minutes. All right, I probably should go faster. And we have 0 is equal to gamma e MEVC minus momentum of the neutrino times C. again assuming it's massless. So what are we trying to solve for? We are trying to solve for energy of the electron. So we're trying to find this. It would be nice to... So let me simplify some of these things, because I think it makes it appear as though I have two unknowns here with the neutrino, but that's actually not the case. With the neutrino, because the momentum of a massless particle is its energy divided by c, I can use that there. So this should be energy divided by c. So yeah. So what it should be is energy divided by c, and this is for a single neutrino. I'll have two of them going basically in the same direction, so let me double it. Then c is cancel, and I have that. Okay, so I think it'll be worthwhile to do some rewriting, because it still looks like I have one unknown, two unknown, three unknowns, and that's actually not the case. There's this energy, this relationship that we can use. So I think so introducing beta, we have v of e, which is beta times c squared, and we have gamma of e, which is 1 over square root of 1 minus beta squared. So let me do this. I'm going to do this substitution here, and instead of substituting this in there, this is what I'm going to do. I'm going to solve this for beta. Actually, is that what I'm going to do? This is what I'm going to do. Sorry. It took me a while to remember what I usually do. That minimizes the algebra as much as possible. So I'm gonna, from here, I can get beta is equal to square root of 1 minus 1 over gamma e squared. So I'm gonna actually plug this in, beta as v over c. So doing the substitution, this is what you end up with. So gamma e times me, and for beta, I have square root of 1 minus 1 over gamma e squared. And because this is v over c, now I'm multiplying by c squared. Now imagine absorbing this gamma e into this square root. You see simplification. You see me times the square root of gamma e times 1. So gamma e, bringing e, I get squared. So gamma e squared times 1, that gives you that, minus gamma e squared times this gives you 1. So it's a relatively simple expression that ends up being. So using this, let me rewrite my equations again. So I got this that I can just copy and paste. How am I doing on time? 8 minutes, yeah. All right. And for that second equation, this is what I'm going to have to write. 0 is equal to me c squared times the square root of gamma e squared minus 1 minus 2e nu. Alright, then I think we have only two unknowns. We have the energy of the neutrino that's unknown, and we have gamma e that's unknown. So I think the simplest thing to do is I can just take these two equations and add it. That'll cancel out the neutrino energy, and I can move on from there. Mu c squared is equal to gamma e. Let me factor out me c squared to the right. So it's going to be gamma e plus square root of gamma e squared minus 1 me c squared. So solving for, yeah, all right, it's going to be complicated. So let me do it this way. Solve for gamma e in mu times c squared is equal to gamma e plus the square root of gamma e squared minus 1 times me c squared. We'll finish later. And I want to see and make sure I address some of it. Earliest model, making it possible. What is the minimum energy for the electron in this decay? Same answer. One is same as A above. Electron can have as little energy as its rest energy is equal to me c squared. And what is the maximum energy for the electron in this decay? So, because it's a neutrino decaying into this, so here, the first one, neutrino is carrying away most of the difference in rest energies. And two, if the neutrino carries away basically a zero energy, then the electron will carry away most of the difference in the rest energies. Proton being so much heavier, it won't carry away as much kinetic energy. Because with the smaller energy, they'll have the same amount of momentum as an electron, which is, let me refer up there. So 9.3, let me do this. Just back and forth will waste so much time. So, which is 939.6 MeV minus 938.3 MeV minus 0.5 MeV is equal to, so it's 938.8, so 0.8 MeV. I think that's the maximum electron kinetic energy for total energy of about 1.3 MeV. Alright, how much time? Okay, 4 minutes. Okay, so I think a C is done there. And let's finish up B. So solve for gamma E there. Okay, so yeah, so let's finish the algebra. I think I can do it in 4 minutes. So I'm gonna solve for this first. So that'll be square root of gamma E squared minus 1 is equal to, I got some ratio stuff going on. Move that over, so it'll be mu over me minus gamma E. Square both sides. Oh, I get some simplification. So gamma E squared minus 1 mu squared over me squared. The cross terms, there's two of them, minus 2 mu over me gamma E. This thing squared, that'll be plus gamma E squared, and this is the simplification I saw. Squared terms cancel, thank God. I don't have to use quadratic formula. So I have to solve for gamma E, so I'm gonna move this one over, move that over. Doing that gets me 2 mu over me gamma E is equal to 1 plus mu squared over me squared. So multiply through by what will get rid of 2 mu over me on the left hand side. So it'll be me over 2 mu. So that'll give me the answer for gamma E. Gamma E is equal to me over 2 mu plus doing some cancellations, mu over 2 me. So that gives me gamma E. Let's quickly do that in a calculator. Do I have time? Yeah, 2 minutes, okay. So let's quickly do that. Mass of the electron, 0.511 divided by 2 times mass of the muon, 105.7, plus mass of the muon, 105.7 divided by 2 times 0.511 is equal to, I get 103.43. Okay, so given that gamma E is equal to 103.43 with the numbers above. The total energy of the electron in this decay is equal to gamma E times me times c squared, which is equal to, let me do this calculation. So gamma E times 0.511, so 52.85. So 52.85 MeV. So of the energy that muon had, so muon had energy of muon had 105.7 MeV. So this must mean the difference of 52 point, I can't do this in my head. So let's 105.7 minus 52.85. Oh, difference of 52.85 MeV must have been carried away by the neutrino. I guess given the massive difference between, well, the two masses, electron is practically massless. I think I could have made that argument to say maximum electron energy is about half of the muon energy. Because, yeah, I think that's what it ends up being. So, all right, so that's all submitted. Let me attach my work. And yeah, I guess the whole thing was that. So with the B, I think with a great physical intuition, someone could potentially have answered that question with a fair amount of precision, without relying on all this calculation that I was doing. But it's good to be thorough, I think. Let's see. And after I attach my work, I will double check the answers to make sure that I didn't make any mistakes. Or, if I did make a mistake, I'll correct it within this session so I don't have to make another video or, do an editing. So I can put in corrections when I edit the video. I usually put in some text title correcting the error, but those are never as easy to notice as someone saying audibly out loud. So I'll save work and continue, and all the scores will be 0 because they are all manually graded when they are graded. So okay, I'm gonna bring this up in my instructor view, and then we can bring up the answer key and compare my sleep deprived answers with the answer key answers, where hopefully I wasn't programming in the answer key while I was sleep deprived. So, all right, I got the test stuff. So this is my current submission or current test submission. Okay, what is the minimum energy? Let's hope. Yeah, it's rest energy. Yeah. So, yeah, too many particles carry away in a way that conserves momentum. Yeah, just go opposite. Okay, what is the maximum energy? I calculate 52.85. Is it? So yeah, this is the setup, and doing all this calculation. Yeah, 52.8, about half of the muon's energy. Yeah, and I think again, this is something that someone could have guessed by looking at the rest energies of the electron and muon and realizing, oh, muon is something like 2,000 times, that's 200 times as massive as electron. And given that if we approximate electron as being massless, it's going to be a pretty good approximation. That's something that someone could have figured out. That's, I think, the same approximation I did in the next question, actually. So yeah, the answer I figured out is the correct answer. I think here I rounded wrong. It should be 52.9 or 85. All right, and this, let's see. That was my answer. And the minimum, same as, yeah, A above. It can be created at rest. For the maximum electron energy, can it not be? Yeah, but I thought, well, let's see if this argument is roughly right. I think it might still be right. Yeah. So I mean, you can do all this, but I had a good physical intuition, and the physical intuition I had was that because basically that given that proton and neutron are both so much more massive than electron, that I can treat electron as being basically massless. If electron is massless, or how do I put it? So I guess this is where my intuition comes from. So if you look at relativistic energy, gamma mc squared, and relativistic momentum, gamma mv, it's the question of for a given amount of momentum, how much energy should I have? I guess let's do it this way. So we are going to be in the low momentum regime, so non-relativistic regime. There I can talk about kinetic energy, which is 1/2 mv squared, or rewritten p squared over 2m. So for something that has a larger mass, you can have the same p, same momentum, with a negligible amount of kinetic energy. As m goes to infinity, same p, kinetic energy becomes negligible. So the physical intuition I had was, well, proton mass is so much greater than electron mass, so I can have a proton carry away however much momentum it needs to balance momentum being carried by the electron, and in that process the proton will basically carry away zero kinetic energy, or close to zero. And proton carrying away basically zero kinetic energy means I can have electron carry away all the remaining kinetic energy. And doing that argument and the calculation got me this. This is the kinetic energy that electron can carry. So add that to its rest energy, 1.3 MeV. And that does end up giving you the same answer as if you went through this detailed calculation, figuring the Lorentz factor for proton, Lorentz factor for electron, do all that, and you get the same answer that I got in like 2 minutes. So anyways, that's it. That's for this. Let me know of any questions. I guess one benefit, it's been like 2 weeks, so I don't remember which question I loaded the dice with. We'll see. Start. Okay. Large Hadron Collider, right. It stands collide with enough amount of energy, right. Lower beam, enter text sensors. For each proton in the beam, find the numerical. So this is where knowledge of some of the dynamical quantities will be helpful. Let me just write some of those things down. So we have definition of beta as V over C. Gamma in terms of beta is 1 over square root of 1 minus beta squared. And you can write beta in terms of gamma. beta in terms of gamma is square root of 1 minus 1 over gamma squared. So with that, some of the expressions, like for energy, the total relativistic energy is gamma mc squared, and total relativistic momentum for a massive particle is gamma mv. And the final expression that's sometimes useful, like if you ever want to find a quick expression for velocity, then the thing that'll give that to you is pc divided by e. You can kind of look at this expression here, and then multiply this by c and divide by e. What I would get is gamma m's cancel out, and I get v over c or beta. So that's what I have in my head. So in A, it's asking for the numerical value of gamma. And they've given us the beam energy. For A, they've given us the beam energy, by which I'm assuming that they mean the total energy, the kinetic plus rest energy of the proton beams. That's 7 times 10 to the 12 eV. So looking at this expression for energy, this is what I notice. It's got gamma in it, and everything else is constant. M is constant, like rest and rest mass of the proton, of which I'm given 10 to the 9 eV per c squared. See, that's constant. So if I'm given energy and I want gamma, I can do it super quickly this way. I can say, oh, looking at this, I can say from 1 that gamma is equal to the total energy minus mc squared. So that would be 7 times 10 to the 12 eV divided by that approximate value of 10 to the 9 eV. I see some nice cancellations, which is why I do it this way. 7 times 10 to the 3 eV or 7,000 eVs cancel out. So yeah, that's really simple. Gamma is equal to 7,000. And it says find the numerical value of V to at least 3 significant figures. Oh, that's a mistake. V is equal to C. 3 significant figures. This is what I mean. So let me use this formula to actually calculate it. I think I can do it this way. Do I have time to waste? Maybe. Let me do it after. Justify it after. Waste time without first knowing I have time to waste. Another source of high energy particles is cosmic rays, where high energy have been detected. One may ask, why don't we use cosmic rays, right? The two So what it's trying to say is you got two different setups. There's the collider configuration, which is the LHC configuration. You have two particles that are coming in with more or less the equal energy towards each other. And the other would be stationary target picture, which is more appropriate with something like cosmic rays. Wait, not CMB. That's referring to something else. Cosmic rays. So in that case, I couldn't remember. In that case, one target is stationary and the other proton is coming in with some amount of energy that's can be related to the other, but is going to be different. So with those pictures in mind, it's asking, let's correctly compare the physics of LHC collisions with the physics of cosmic ray collisions. Find the beam energy of LHC in the reference frame where one of the two colliding particles is at rest. Okay, so I think this is how I want to label it, and this is probably how I labeled it in the solution. I'm going to call this my frame S, and I'm going to call this my frame S prime. And this is the frame that you get if you imagine kind of a box around this that's moving to right with the speed v that we calculated above. So this frame is moving at the same speed that the rightward propagating proton is. Then in this reference frame, this is at rest. V prime is equal to 0. And this, with the energy EB prime, it's moving at some speed, V prime. That's still going to be approximately C. That doesn't give you a lot of information. So you have these two different reference frames, and what you have to do is you have to do Lorentz transformation to go from one frame to the other frame. And this is where you really need to use the fact that energy and momentum form four vectors. I covered this in lecture, which your textbook doesn't. Energy, momentum, four vector. I'm just going to write the time component and the x component. Nothing interesting happens in y and z. So this four vector, of which I'll write the first two components, looks like the time component is energy divided by c, and the position component is the momentum. And once you identify this as a four vector, this is the useful thing. It transforms under Lorentz transformation, like coordinates do. So because it transforms under Lorentz transformation, like coordinates do. Sorry, 1 second. I'm gonna pause the recording for a bit. I just saw a call come in that might be important. I'm gonna pause the recording and then I will restart the recording in a bit. Recording in progress. Okay, sorry about that. Oh wait, am I gonna run out of time? Let's see. If I run out of time, I might just go through this quickly. Sorry, I had to take care of it. Recording is resumed. Timer's run. I'm gonna use Lorentz transformation so that it's so let me actually do this relatively quickly because I think I'm gonna run out of time. So what I need to say is that the energy and momentum in the S frame S prime is going to be the Lorentz transformed quantities of the energy and momentum in the frame S. And I have to be careful here. So if I look at the rightward traveling particle, I'm going to get something boring, zero energy. So I need to be looking at this particle here so that I'll get this particle here with its energies. So when I do this calculation, this is what it looks like. It's asking for what? The work. Find the beam energy of the electricity so I'm looking for this quantity here, E prime. So it's going to be so E prime is equal to, I'm just gonna do some of the algebra in my head. It'll be gamma E and then minus gamma beta pxc. And when I plug in the numbers, the energy will be 7 TeV. And when I plug in number for this, it's going to be minus 7 TeV per C. So the whole entire set of numbers will be this. The gamma from previous was 7,000 times 7 TeV. That will already make the numbers large. And then my gamma here is still 7,000. And then beta is more or less 1 because it's more or less the speed of light. And then this will now be minus 7 TeV per C times C. C is cancel. So it's basically going to end up being 2 times 7 times 7, 49,000 TeV. Or doing the calculation in my head, EB prime is 9.8 times 10 to the power of, let's see, 1, 2, 3, 4, and then 12. So 10 to the power of 1, 2, 3, 4, 16 EV. Yeah, good. So you might have expected this times factor of 2 from two particles, and what's quite surprising is just how much boost you get from the relativistic factors. Okay, how much time do I have? 5 minutes. Let's consider different scenario. One of the friend off. Am I gonna have? I might not have time to finish that after I had to answer that call. What is the maximum? Okay, okay. So for C, this is the setup. Um, we have so one particle is at rest, and I know the beam energy of the other incoming particle. That's still 70 eV. So we have to. Let me give you a shortcut. So when it says so what is the maximum mass such a particle can have? Really, what I'm looking for is when this collision occurs and there's some colliding thing, I'm asking what is its mass? And it more specifically, what is its invariant mass? And there's a really convenient formula that comes from the energy momentum relationship, which is that invariant mass squared c to the fourth power is given by or let me be careful with the factors of c. Or actually, let me not be careful because this is how I would normally do it. M squared is equal to E squared minus P squared. So in my lab frame, I have my total E is equal to the proton rest energy 1 GeV plus the beam energy 7,000 GeV or 7 TeV. So it's basically 7,000 still, and momentum is now going to be uh, minus 7,000 GeV per C. So the invariant mass here. Um, so I can plug in the numbers here. Let's see. Host calculator. So E squared is going to be time 3 minutes. E squared is going to be 7,001 times 10 to the power of uh, 12 electron volts squared minus 7,000 I mean there's minus, but 10 to the power of 12 wait GeV giga, that's 9 um, 9 squared. So when you do this calculation you get the answer of 1.6. Did I do something wrong? Might have done something wrong. I'm in a hurry and I'm making mistakes. Yeah, so I'm not going to be able to finish this in the time. So let me just copy this off and let's just finish it up. Finishing it up after time. And I think in trying to take a shortcut, I probably made a mistake. So um, use time dilation t is equal to gamma times tau. Um, so let's start by first correctly specifying um, the time is the energy momentum four vector for the collision picture. So we have still the same picture, momentum, the energy of 1 GeV, it's at rest, and I have another particle that's coming in with energy of 7,000 GeV. And the momentum for this particle will be momentum will be basically It'll be very close to 7,000 GeV per C. But it might be that I can't do that approximation. Let's see. So the energy momentum for vector E before is going to be um, the the 1 GeV per C 0 plus 7,000 GeV per C, and then I think I can still use ultra relativistic approximation, which is to say this is minus 7,000 GeV per C. Then the total is 7,001 GeV per C minus 7,000 GeV per C. And really the statement of conservation of energy is that this is still equal to energy after. And when you have this energy after the, or energy momentum for vector after the collision, um, the way you would calculate, so this is the term for E over C, and this is the term for momentum. The way you would calculate mass is from that energy momentum relationship. The E squared is equal to m squared c to the fourth power plus p squared c squared. And when you solve this for the invariant mass, you get m squared is equal to um, e squared over c to the fourth power minus p squared over c squared. Dividing through by c to the fourth, 2 cancels, yeah. So the numbers you have here will be, let me see, if I keep everything in giga electron volt unit, I think my final unit will be fine. So my initial energy is, my energy is 7,001 giga electron volt, square that, minus the momentum 7,000, or minus the 7,000 squared. And what do I get? Oh yeah, I think that makes sense. Yeah, I think I had trouble interpreting the number, that I missed this power of 10. I think that's what that was. Yeah. So that's the rest energy. Now I can take the square root of that. That'll give me in giga electron volt. That's the m squared. So when I take the square root, I'll get rest mass. Yeah. So from that calculation here, what you have is m is equal to 118 GeV. So that is the rest energy of the. So this is the max rest energy of particle produced from 7,000 GeV beam. And notice the difference. This 118 out of 7,000. That's only what percent? So only 1.7% of the original energy. So much of the energy still remains as kinetic energy because the momentum had to be conserved. And so the second question was what? Suppose that above has improlonged lifetime, in the left, right. Yeah, so how long does the particle live before decay? So you have to calculate the gamma factor. And the easy way to calculate gamma factor here is, now that you know the rest energy of the particle, you can go back to using the formula we used way up in part A, which was that given that energy is given by gamma mc squared, whenever you need the gamma factor and you know the energy and mass, you can say gamma factor is E divided by MC squared. So here it's going to be 7001 GeV divided by 118 GeV, and then I will multiply by C squared. So it'll be 7001 divided by 118. So gamma factor of about 59.3. So if the particles the particle's proper time lifetime is 2 microseconds, its a time dilated lifetime will be that times this. So it'll be the time dilated lifetime would be about around 120 microseconds. So yeah, so that's the answer. And I will do the calculation of times after the session. Because I was on the phone for that amount of time. I don't know if with all this I actually did finish it before 20 minutes were up or not. And so that's the kind of how I would have ended it, except I had to answer a phone call. Let me go back to what I was doing in A there. Yeah. V is equal to C, justify later. So this is how I was going to justify it. So I have this formula for beta in terms of gamma. Let me plug that into my calculator. So beta square root of 1 minus 1 over gamma, which is 7,000 squared. When I do this calculation, you'll see that it is, I think it's easier to express it this way. Let me do 1 minus this. And it'll give me the number in a scientific notation. In one part out of 10 to the 8 is how close it is to 1. So if they say to at least 3 significant figures, yeah, to at least 3 significant figures, this number is 1. That's why V is equal to C is right. If they wanted a number different from 1, either they had to say that they want a number different from 1, or they have to give 1, 2, 3, 4, 5, 6, 7, 8, 9 significant figure specification. So then we'll say that go down to 8, 9, where it rounds to 0. So it'll have like 8 nines, and yeah, they didn't say that. That's why this was fine. And this is something called this is under what's called ultra relativistic regime. Let me just write it here. So that's the regime where gamma factor is so high. Ultra relativistic regime. That's where the gamma factor is so high that that you can just you can just use this approximation. V is equal to C. So let me attach all of this and then wrap up this session here.